In general, producers of the metallic powders are not the same companies as those that make the metallic powder parts. Now, we have the suppliers that they produce the powder and then supply it to the manufacturer, to the plant that manufacture the components out of that powder metals, and those called customers. It's therefore appropriate to separate the discussion of the powder production that we will discuss in this section from the processes that used to make the product from the powder metallic. So again, we have powder. We need to produce this powder separately, which we call by suppliers. Then we can take the powder and make the products and the parts out of the metallic powders, and those are the customers when we talk about the metallic powders. Now, when the customers take it and make products, then it becomes supplier to another customer. Virtually any metal can be made into powder form. There are three principal methods by which metallic powders are commercially produced, each of which involves energy input to increase the surface area of the metal. The methods are the atomization, chemical, and the electrolytic. In addition, we also have mechanical methods that are occasionally used to reduce the powder size. The first method we will talk about of how to produce the powders is the gas atomization method. This method is based on the conversion of molten metal into a spray that solidify into powders. So we have metal. That metal we should first molten it, and then using a high velocity gas stream that flow through the nozzle, take the molten metal, spray it. During the spray, it will turn into solid powders. We can use water instead of gas for the atomization method, which is very similar to the gas method. And here we have high velocity water streams that flow through the nozzle. We have water from this side, water from this side, and again we have the molten metal. And we can see that it will solidify and turn to metal powder. The water atomization method is more commonly used and is specifically suited to metals that melt below the 2900 Fahrenheit. So in this case, the cooling is more rapid and the resulting powder shape is irregular rather than spherical. This is one of the examples here, which is an iron powders that are produced by water atomization. You can see that the particles are not regular and we have different shapes. The other two types to produce the metallic powders, which is the chemicals and the electrolytic, you only need to know the names of these procedures. You don't have to know all the steps and procedures. So just focusing on the atomization with its two types, the gas and water. Now, after producing the metallic powders, we need to use that powder to make products and parts. This step is called the conventional pressing and sintering. The conventional PM sequence consists of three steps. The first step is blending and mixing of the powder. Then next step, compacting, in which the powders are pressed into the desired part shape. After get the desired part shape, we have the sintering, which involves heating to the temperature again below the melting point to cause the solid state bonding of the particles. So after that, in addition, we have other operations called secondary operations, which sometimes performed to improve the dimensional accuracy, increase density, or any other reasons. But these are the three main steps or in the process: blending, mixing powder, compacting or pressing, which is applying high pressure, and then applying heat to get the desired shape. So again, this is the steps. The first one, blending and mixing, then compacting, and last thing is sintering. After each of these steps, we are trying to make the particles of the powders as close to each other as possible, and the shape as accurate as possible. Before the compacting and sintering processes, and in order to achieve successful results, the metallic powders must be thoroughly homogeneous beforehand. So we have two main steps that we need to do. The first one is a blending, which is when powders of the same chemistry but different particle size are blended together, and that would reduce the porosity of the powder. And then we have the mixing here, when we mix different types of metals together. And this is one of the advantages of using the PM technology or processes, which give the opportunity to mix different type of metals into one a product, which would be difficult or even impossible to produce by any other type of a process. After the blending and mixing process, we can go ahead and do the compacting. The compacting, high pressure is applied to the powders to form them into the required shape. So the conventional compaction method is pressing, in which opposing punches squeeze the powders in a die. Now the work part after pressing, called green compact. We have the green compact, which is the part or the product after pressing but not sintering yet. And that's why we call it a green, which refers to it's not yet fully processed. In the same way, we call the strength of that part green strength, which is the strength of the part when pressing is okay by handling, but far less than what it should be after the sintering. This is the steps of the conventional pressing. The first step is filling die cavity with powder, which is similar to the casting when you fill it with molten metal, but here again it's a powder. Then step number 2 is the initial position of upper and lower punches during the pressing. We have start the pressing. This is the initial position of the upper. So we have two punches. This the upper one, and this is the lower one. The last or the final position is in step number 3, which we can see that we applied more pressure in two sides, from upper side and lower side, and we can see that the product here is smaller in size, but it have higher density and the particles closer to each other compared to the initial position. The last one step is the part ejection. So we release the pressure and the part is ready, not fully processed, but and that part which called the green compact. You can say here is the green compact. Excuse my handwriting. That photo is for a hydraulic press for conventional pressing. The third and last step is the sintering. After pressing, the green compact lacks strength and hardness, so we need to improve the strength and hardness of the product by heat treatment, which bond the metallic particles. Usually, we reach a temperature of 70 to 90% of the metal's melting point, and generally agreed among researchers that the primary driving force for sintering is reduction of surface energy. And the part shrinkage occurred during the sintering. It happened due to pore size reduction. This is the sequence of sintering when looking through a microscopic scale. We can see in the first picture here the particles and the point bonding between these particles. The particle bonding initiated at contact point. Now the contact point in the next step grow into necks. We have here points, then it's grow a little bit into necks. The other step is pores between the particles are reduced in size. We can see that the pores or the small spaces between the particles reduced in size, and the particles get closer. The neck here also is expand. You could have thick or long connection between the particles. The space is reduced, or the pores. Now last thing is that the grain boundaries developed between the particles in place of necked region. We have here boundaries. The neck is converted into boundary, and we have very small pores. The size of the spaces between the particles, it's very small. And this is the end of the sintering steps. Sometimes after the sintering, we need to do other operations or other steps, which called secondary operations. Since we get the final product, the shape and size, dimensions, but we need to make more improvement. Maybe we need to increase the density, improve the accuracy, or accomplish additional shaping. That's why we need to do secondary operations. We have different types of secondary operations. Let's start with the densification and sizing. Here we need to apply pressure again, which is called repressing. So we have pressure, heat, and then pressure. Pressing in closed die to increase the density and improve the properties. The sizing is pressing to improve the dimensional accuracy. So we have the correct dimensions, but you remember in chapter 4 we talk about the dimensions and the accuracy. In some applications we need to improve the accuracy. That's why we use the sizing process. We also have coining, which is pressing details into its surface. We have the correct surface, correct dimensions, the correct amount of density, but we need to add details into the surface, like the coin have details. That's why we call it coining. The last one is machining, which for geometric features that cannot be formed by pressing, such as adding side holes or threads. That's performed using machines called machining. The other type of the secondary operations called impregnation and infiltration. We in the previous video talked about the porosity and why it's important in terms of the PM characteristics. So the porosity can be exploited to create special products if we fill that available space with oils, polymers, or even metals. The first one, impregnation, it's occurred when we fill oil or other fluid into these spaces, for example gears. The other one is infiltration, and that's when we fill the spaces with molten metals, and we use this process to increase the density, so we don't even want these small spaces. We fill it into we fill it with molten metal to increase the density and the strength of the product. The pressing and sintering techniques are the most widely used shaping technology in powder metallurgy. However, we have some additional methods that used to produce the PM parts. The first method is the isostatic pressure or pressing, and in this method we applying, instead of apply pressure, we apply hydraulic pressure and from all directions of the part to achieve the compaction. The other type is the powder injection molding, and here we're starting with a polymer that have 50 to 85% powder content, and then the polymer removed and the PM part is sintered. The other type is the powder rolling, extrusion, and forging. So here we have the powder rolling, we have the feeding of the powder. Start from here, the first step, and then we can see the rolling steps, then applying the heat, cold rolling, heat, and then the final product. This is for sheets and plates or flat products. The energy required to use the metal and produce powder form out of the metal is high and need additional steps. That's why it's producing of the powder is more expensive than any other metal working. Now, the PM is only competitive in certain range of applications. That's why we say it is good for high production rate and in some medium production rate. I want you to think about what are the materials and products that seems most suited to powder metallurgy. I want you to do some research about materials and products produced using the powder metallurgy, and you can write your notes on a sheet of paper. On Wednesday, the beginning of the class, we will discuss this together before we start with chapter 16. These are some of the product design guidelines that will also help you answer the question. So the minimum quantities that needed to justify the cost of the equipment and special tooling is at least 10,000 units. We talked about the porosity and how the PM is unique because it's capable to actually fabricate parts with controlled level of porosity. The PM can also make parts out of unusual metals and alloys. So when we talked about the mixing step and how we can mix different materials, the powder of different materials before we start the process. Then talked about part geometry that must have vertical or near vertical sides, and trying to avoid features on part sides like holes or undercuts, because that's will need another step after the PM procedure. These two examples, the first one is about the side hole and the next one is the undercut, and these two features should be avoided in the PM since the part ejection is impossible. Now, other guidelines like the screw threads cannot be fabricated, so they must be machined into the part. That's why we need additional step. The chamfers and corner radii are possible, but the problem occur in punching the rigidity when angles are too acute. The wall thickness should be at least 1.5 millimeter between holes or a hole and outside wall, and the minimum hole diameter should be at least 1.5 millimeter. So in terms of the chamfers and corner radius or shapes, this figure here have some examples of what is recommended and what is not recommended. So you can see in the first two figures, A and B, for example, the acute angles are not recommended. Instead, we can work on larger angles. The inside radius is acceptable, but the outside corner radius is should be avoided, and the radius that combine radius with chamfer is also preferred. So here the combination of radius and chamfer is okay. Using outside corners it's not recommended. Using also small angles or acute angles is not recommended, but we can use larger angles and we can use inside radius. So here now we finished chapter 15. If you have any question, you can send me an email or ask me on Wednesday. On Wednesday we will start with chapter 16, which is processing of ceramics and cermets. You can see we will have some similarities between chapter 15 and 16. Thank you for listening and see you on Wednesday.